A modern smartphone is engineered to push an aggressive, continuous wave of electromagnetic energy outward to connect with distant cell towers. To measure this baseline capability, engineers calculate total radiated power, or TRP, in a perfect free space environment. This photograph shows an HTC smartphone resting isolated on a pedestal inside an anechoic chamber, aligned by a red laser to prevent outside interference. In this setting, this GSM 850 MHz device transmits at a maximum power of 33 dBm. That equals 2 full watts. But a laboratory chamber is empty. In physical reality, a phone is held tightly by human hands and pressed firmly against a human head. This test reveals the result of that interaction. When held in that normal, everyday position, the actual efficiency of the device drops to less than a third of 1%, exactly 0.29% efficiency. It is a near total collapse of the signal. This is the core paradox of mobile engineering. A device built to output 2 full watts essentially fails in its primary intended physical use case. To find where that energy is going, we must dismantle the variables causing this degradation step by step. Tracing the path of this 0.29% failure state is the only way to see if the signal can be saved through internal adjustments or if the solution requires a change to the phone's physical architecture. Let's return to the isolated free space measurement to establish our absolute ceiling. Without any human interference, this handset operates at a maximum starting efficiency of 78.35%. The first vulnerability in maintaining that efficiency is physical architecture. This diagram points exactly to the primary cellular antenna location, housed across the bottom edge of the device. If we introduce the first experimental variable, a human hand, avoiding that antenna zone, the interference is immediate. The inset on this wide shot highlights a grip keeping the palm away from the bottom edge. Even with careful spacing, efficiency immediately falls to 34.91%. The physical reason for this drop is that human tissue acts as a lossy dielectric material. The dense volume of water inside of human flesh naturally absorbs and scatters the outbound radio frequency energy. This absorption happens even when the skin isn't touching the actual radiator. Just placing a hand within the near-field range of the antenna warps the electromagnetic field. Losing over half the signal, dropping from 78% to 34%, just by holding the phone is a major design flaw. But the data gets much worse. Human tissue inherently functions as a localized signal jammer. Because of this, ergonomic design must prioritize physical distance from the antenna. This brings us to the most common user error, directly covering that primary antenna location. In this hand-covered configuration, the inset clearly shows the user's palm fully cupping the bottom of the phone, smothering the radiator. Direct hand coverage plummets the efficiency down to 3.16%. This is a physics problem known as dielectric loading. When you make direct physical contact, you detune the antenna's impedance matching. The signal is choked out and absorbed by the fleshy mass before it can radiate away. The final fatal variable is taking that detuned, smothered antenna and pressing it directly against a massive dielectric object, the human head. That brings us back to our baseline failure state, an operating efficiency of 0.29%. This waterfall chart visualizes the absolute scale of the loss across all 4 variables, starting at 78% in free space, dropping to 34% for proximity, 3% for direct coverage, and flatlining at 0.29% for normal use. Modern smartphones often attempt to fix this with active software tuning, aggressively pumping more power through the choked antenna to compensate for the user's bad grip. But trying to overpower human dielectric loading with software is incredibly inefficient. The problem is physical, which means it requires a mechanical intervention. This brings us to U.S. Patent 9698847, a hardware design approach explicitly aimed at solving this near-field interference problem. The core philosophy of this patent is straightforward. Instead of fixing the signal, fix the user's hands. This 3D render illustrates the physical form factor of the global wireless technology device. The design relies on altering the exterior geometry of the handset. This exploded view highlights the push-in, pop-out protrusions mounted on all four corners. When a user attempts to grip the phone in a real-world scenario, these corner protrusions physically block their fingers, automatically forcing them away from the primary antenna zone. This forced physical displacement creates a guaranteed air gap between the lossy dielectric tissue and the radiator. Because this is a passive mitigation strategy, it draws no power, requires no software algorithms, and avoids complex impedance matching circuitry. By altering the layout at the corners, this design also protects the Wi-Fi and Bluetooth arrays typically mounted near the upper edges of the device. By treating radio frequency degradation as a mechanical layout problem rather than an electrical tuning problem, engineers can guarantee a baseline level of antenna clearance regardless of the user's habits. Testing this mechanically enforced holding configuration inside the anechoic chamber yields radically different data. Looking closely at the inset, the hand is completely bridged away from the chassis, resting strictly on the protrusions. This specific grip immediately recovers the antenna efficiency up to 16.06. Furthermore, this passive constraint drastically reduces the workload on the phone's internal amplifiers, saving battery life that would normally be wasted pushing through physical interference. We started with the paradox of a 2-watt machine failing at a fraction of a percent, proving that human biology is the ultimate disruptor of electromagnetic fields. In the highly complex world of mobile RF engineering, sometimes the most effective way to optimize a digital signal is simply to build a physical wall between the antenna and the human body.